Welcome back to the module covering the nuts and bolts of the control plane. In this lesson, we will explore different SDN controllers, and we'll talk about the trade-offs of using one particular controller or another. By the end of this lesson, you should have a little better understanding of the trade-offs of different SDN controllers, and you should be a little bit better informed about which controller may be appropriate for the problem that you're trying to solve. In this lesson, you'll get an overview of different SDN controllers, and by the end you should have a basic understanding of each controller. In particular, the concepts that underlie the design of a particular SDN controller, the architecture of that controller, and the programming model that that controller uses. We'll talk about the advantages and disadvantages of each particular controller we talk about, and also the ideal situations for using a particular controller. To help you better, there are many different SDN controllers in the wild, and it's somewhat of a joke that there are almost as many SDN controllers as there are SDNs. So we obviously won't be able to cover them all in this short lesson, but I just wanted to list out a few to raise your awareness. One is Knox and Pox, and we'll talk about that in today's lesson. We'll also talk about a controller called Ryu, and we'll talk about a controller called Floodlight. There are some additional controllers that we'll cover in this course in later modules. Pyretic is an SDN controller that's effectively a policy layer for SDN, and Frenetic is a similar controller that's written in OCaml. Procera is another policy layer for SDN that we'll also cover later in the course. And RouteFlow is an SDN controller that's specifically geared towards SDNs that are interested in interdomain routing. Let's now jump in and talk about the different considerations that you may have when choosing a particular controller. One consideration you might have is the programming language that the controller is written in. This, of course, affects how comfortable you are writing programs for that controller, but it can also affect the performance. Another consideration is the learning curve. How difficult is it to learn to write policies using that particular controller architecture? A third consideration might be the user base and community support. How active the developers are in maintaining that controller and how many users that particular controller has. The number of users who are using that controller or developing on it can be important because that community effectively serves as a base of support for you when you're developing your own policies and control programs. Different controllers also have different areas of focus. The controllers that we'll talk about in today's lesson are mostly a re-implementation of what's called the southbound API. That is the protocol or API that's used to speak directly to an OpenFlow switch. In later lectures, we will look at some controllers that implement what is called the northbound API, or a policy layer. These types of controllers, such as Pyretic, Procera, and so forth, allow a network operator or an SDN programmer to write more complex, high-level programs at the expense of not being able to meddle directly with flow table entries, at least not as a general rule. Different controllers also have different goals. Some are very focused on supporting production networks, whereas others are more focused in supporting rapid prototyping efforts. In the rest of this lesson, we'll take a closer look at the 4 SDN controllers that are highlighted here. We'll look at Knox and the Python variant of that, Pox, Ryu, and Floodlight. Knox is a first-generation OpenFlow controller. In fact, the early version of Knox was the first OpenFlow controller. Knox is open source, it's stable, and it's widely used. There are 2 flavors of Knox, one called Knox Classic, which is written in C++ and Python and is no longer supported. The new Knox is C++ only, it's fast, it has a clean code base, and it is well maintained and supported. Users implement control applications in C++ when they are developing for Knox. The Knox distribution supports OpenFlow version 1.0, and there is a fork called CPQD that supports OpenFlow versions 1.1, 1.2, and 1.3. The programming model is very similar to that of many OpenFlow controllers, in which a controller registers for events, and the programmer then writes event handlers that take specific actions or perform various tasks when those events are raised. There are a number of scenarios where it's appropriate to use Knox. One, of course, is if you already know C++ and are comfortable with it. The second is if you're willing to use very low-level facilities and semantics of OpenFlow. Knox is a bare-bones implementation of the southbound API, and it does not provide many high-level abstractions. This may be useful, of course, if you want to meddle directly with the southbound API and extend it. A third reason to use Knox is if you need good performance. POX is essentially Knox in Python. It supports OpenFlow version 1.0 only. It has several advantages. One is that it is widely used, maintained, and supported, and another is that it's relatively easy to read and write code. The disadvantage, of course, is that because it's implemented in Python, the performance is certainly slower than Knox. So when might you use POX? Well, if you know or can easily learn Python and are not concerned about controller performance, POX might be the right choice for you. It is a very useful tool for rapid prototyping and experimentation, and hence it's very useful for research, experimentation, demonstrations, and so forth, as well as for learning SDN concepts. And that is one of the reasons that we are using it as the main controller for the assignments in this course. Ryu is another open source Python controller. It supports OpenFlow 1.0, 1.2, 1.3, and various Nicira extensions, and it also works with OpenStack. OpenStack is a cloud operating system that controls storage, compute, and networking resources in a data center and allows you to write cloud applications on top of that operating system. It's open source and has a very large developer community. Ryu aims to be an operating system for SDN, and it has various advantages, including integration with OpenStack and support for OpenFlow 1.2 and 1.3. Again, the disadvantage is that because it's implemented in Python, it has relatively slower performance than some other controllers. Floodlight is an open source Java controller that supports OpenFlow 1.0 and is a fork from the Beacon Java OpenFlow controller. It's maintained by Big Switch Networks. Some advantages of Floodlight include very good documentation and integration with the REST API. REST is a particular software architecture developed by the World Wide Web Consortium that is often used in various client-server architectures. If you're already familiar with the REST API, performance, Floodlight might integration be a reasonable choice for a controller. Arguably, one of the disadvantages of Floodlight is that the learning curve is somewhat steep. So you might want to use Floodlight if you already know Java, if you need production-level performance and support, and you'll use the REST API to interact with the controller. In summary, the choice of controller depends on the various needs you have for integration with various features, your comfort with different programming languages, and your need for performance, as well as your need to support the latest versions of the OpenFlow protocol standard. So this lesson, of course, did not cover all SDN controllers. We mainly focused on controllers that are re-implementations of the southbound API in different programming languages. Next week, we'll talk more about SDN controllers that provide support for northbound APIs, or policy layers that sit on top of lower-level SDN control channels.